Welcome DIKWP, 小工 aboard. Your learning journey starts now. Ever heard of a math problem so simple, even a kid could understand it, yet so darn tricky that mathematicians have been scratching their heads for over 80 years? That's the Collatz conjecture. Pick any number. If it's even, you have it. If it's odd, you multiply by 3 and add 1. Keep going. The guess is, no matter where you start, you always end up at 1. Sounds easy? It's not. So, why is this seemingly simple game such a headache for math? Traditional number theory, our usual toolkit, gets totally lost. Think of the sequence: 6 becomes 3, then 10, then 5, then 16. It's like a wild ride. Numbers shoot up with the 3n plus 1 rule, then plummet with division by 2. This constant bouncing around, this lack of a steady downward trend, makes it incredibly hard to prove using standard methods. It's like trying to predict a hyperactive puppy's path. Even the great Paul Erdős, a math legend, said we're basically out of tools for this. We've checked billions of numbers, they all obey the rule. But that's not a proof. A proof needs logic, not just brute force checking. Okay, if the old tools don't work, let's grab some new ones. Imagine putting these numbers under a special microscope, the DIKWP framework. Think of it as layers of understanding. First, data, just the raw numbers, 6, 3, 10, etc. Then, information. We see patterns like the odd-even dance. Knowledge. We form a hypothesis, maybe all sequences eventually hit one. Wisdom. We ponder the deeper meaning, like how complex things simplify. And finally, purpose. What's the goal? Reaching one. By looking at Collatz through this lens, from raw data to underlying purpose, we start seeing it not just as a calculation, but as a dynamic process with meaning. It's like giving the numbers a voice. Now, here's where it gets really interesting. Let's talk about semantic tension. Think of the odd step, 3n plus 1, as creating tension or complexity. The number jumps, but the even step, n divided by 2, acts like a release mechanism, calming things down. It's like stretching a rubber band odd and then letting it snap back even. This constant cycle of tension and release drives the sequence towards simplicity. And here's a cheeky idea inspired by the bug theory. What if those big jumps caused by odd numbers are like little glitches or bugs in the system? Well, guess what? The subsequent even steps always seem to fix them, pulling the sequence back towards 1. It's like the system has a built-in bug detector and repair crew. This interplay might be the secret sauce, keeping everything converging. So, what's the big takeaway from all this? Looking at Collatz through this semantic prism reveals a beautiful pattern. From complex, chaotic beginnings, following simple rules, things inevitably simplify down to 1. It's like nature's own tidying up process. This isn't just a quirky math fact. It hints at a deeper principle, maybe even a universal tendency towards simplicity from complexity. And that final number, 1. It's not just a number. It's the ultimate simplified state, the semantic ground floor. So, next time you hear about the Collatz conjecture, remember, it's more than just numbers. It's a story about meaning, complexity, and the elegant drive towards simplicity. Pretty cool, right?